Hi, dear.
Hi, Arkady, how are you?
Oh, still alive. I'm sorry.
It's wonderful.
Okay, so
Great.
then to give you opportunity to experience the full joy of it.
Right.
So, how are you?
Oh, pretty well. Yeah. It's very cold today.
Oh,
It's like minus 30 with wind chill this morning, so
oh,
thought it was best to stay home. Yeah.
I see. Yeah, I should be there, not here, but here it is like usually, it's kind of 16 centigrades during the day, so
Oh,
relatively cold for California, but not.
right, right. Yeah, how have you been doing with all of the rain?
Not where we are. I mean, it's
Hmm.
mostly on the slope where kind of possibility of slides are. I mean,
Right, right.
yeah, and it was some in Montecito, Santa Barbara. It was some, but we are uh, kind of near the ocean, and I mean after highway, so not on the slopes at all. So
Okay,
we are
that's good. So you're safe. Yeah.
yeah. But did you enjoy winter? I mean, like skiing or anything
Yeah, I
specific?
don't really I've been doing some winter biking,
Uh-huh.
cycling. Um,
Oh,
yeah, it's actually been quite fun, biking like on the snow and on the ice. I have studded tires, so
yes.
um, yeah.
Alexei Jung was kind of champion of this. He was
Oh yeah.
into the winter. I don't know if you remember his biking, but he did it all. Yeah. So that's okay. So no, I'm okay. Uh, Yeah, so I see that people are coming, but some people are away, right? I know that Misha
Hi,
is
Arkady.
away.
I've seen
Hi,
you in a minute.
Hello.
hi.
Yep.
Mhm. You have a nice picture. Mhm.
Maybe 3. Yeah, then we can use this. Okay, yes.
So it's that camera in the back there that you can't see, yeah.
Shall we need a
Pointer.
sound stick or
Pointer, yeah. What happened to the pointer, yeah.
yeah.
Yeah, we just always keep on losing the pointer. We've got to stay somewhere. The speaker just because the floor below is identical to this. It's the same floor. There's sometimes seminars there. Right. So sometimes it migrates from there into here. Yeah, it's a bit complicated. So we're just waiting for the pointer, and we'll get going. The pointer.
It was downstairs, but I was right upstairs.
Oh, they might be using it now. Yeah. Oh,
It's only one pointer for 2 rooms. So.
Yeah. We can break it in half. Huh. Didn't think of it. Cut it in half. So let's just wait another minute to see if Kongfeng is coming with something. But maybe we can get started, and then if he comes on the point,
Yeah, I'll just
hopefully he'll come with something. Do I hear him? Probably can just get started. All right, then. Well, it's a real pleasure today to introduce Andreas Helset. Andreas got his PhD at Niels Bohr Institute in Copenhagen in 2020. And after that, he's been a postdoc at Caltech. And actually now he's finishing his postdoc and will be going to CERN in September. And so today we're very happy to have him here, and he's going to tell us about geometry in particle scattering.
Great, thanks a lot.
Thanks, Coach.
That's
Thanks.
the pointer as well.
Good, thanks.
So it's
Perfect, thanks.
great. Yeah, thanks a lot for the invitation. It's the first time for me here in the Midwest. It's a bit cold in California, but otherwise it's good. So I'm going to talk about some ideas where geometry shows up in interaction of particles and in scattering amplitude. So the things we'll be talking about today are these things listed here. We'll start out by defining what we mean by this geometry. It's not a geometry in space-time, but in or the space where fields live. Then we'll connect this to various scattering amplitudes. And we'll also look at some relations between the scattering amplitudes through what's called soft theorems. And then we'll move on to talk about some loop effects to the RG calculations, where again, the geometry is relevant. And as an application of these things, we'll look at a standard model extended as an effective field theory, which captures, say, like heavy physics, like beyond the electric scale. And the collaborators I had on these topics are Cliff Chung and Julio Parmartinez at Caltech, and more recently, Elizabeth Jenkins and Anish Manohar at UC San Diego. And feel free to just stop me and interrupt with questions or comments as we go along. So, yeah. So let's just start with something very simple. Let's consider a field theory of some scalars. And if you have scalars, you can write them in Lagrangian in this schematic form. So we need a kinetic term, which is this two derivative term here. And we can allow for like also more this being multiplied by some scalars. We can have potential, and we can have other things which don't list here. These dots could be like higher derivative operators as well. For example, it could be this operator here with four derivatives, but in general, we won't specify what this is. This is just a way of writing any scalar field theory in this schematic way. The thing that will be most important for us is this coefficient of the kinetic term. That will play like a major role in the following discussion, but in general, this is just a way of writing the Lagrangian. Now, without saying anything about what kind of field theory or giving a backstory to this, there's one property that's universal for all these field theories, namely that you can do field definitions. So a field definition is just change of your field variables. So if you change your field variables, the scalar fields can be written as some other function of the scalar fields, like this. And in this sense, it acts as a coordinate. This is like a coordinate transformation where the coordinates are played by the scalar field. And going back to the Lagrangian we had before, we had not just the field, but we also had this derivative of the field. And under this change of coordinates, this d mu phi changes to d mu phi times this prefactor. And this prefactor is precisely the transformation properties of a vector. So this d mu phi transforms as a vector under field definitions. And with these two ingredients, one can see that this Gij, this prefactor of the kinetic term, changes with these two prefactors, and that's precisely a tensor transformation under field definitions. So just based on these like simple construction, we see that this one is like a well-defined vector, and this is a well-defined tensor. And that's by itself is not sufficient for us to like endow this GIJ with some enhanced meaning, but at least it's consistent with thinking of this GIJ as a metric. At least it transforms in the correct way under field definitions.
There's one of the symbol, one of the phi's is wrong. One should be not there, that in that equation, but that one's okay. No, that equation on the left. Oh, it's not
It's an arrow.
it's an
So I'm doing this arrow just going to change.
Yeah, it's not.
This is going to change. Yeah, with all arrows. Yeah. Yeah, well, just stop me if there are any complaints or other comments. Good. So the thing that the leap now is to say that because this GIJ transforms as a tensor, let's view it as a metric in field space. And if we take that as a starting point, we can just open up the favorite textbooks in GR and calculate descendant quantities, which you can derive from the metric. So if you have a metric, you can calculate the Christoffel symbol, which is simply various derivatives of the metric in this combination here. And from the Christoffel symbol, you can then calculate the Riemann-Coty tensor, which is the one derivative of the Christoffel plus these two Christoffels here. And this Christoffel symbol also gives you a notion of a covariant derivative. So that's like the geometric object that we'll be looking at, which you can derive from the metric initially.
But in principle, the connection of the metric.
Good. Yes, that's good. So, and that's a very good point. In GR, like you can put down some metric, but that's not the same as defining the full manifold. We can endow with some other connection that's not the Christoffel symbol. So you can define some other covariant derivatives that deform the version of this.
So here we're assuming the same geometry.
Right.
Compatibility or something.
Yeah, so like this definition will impose metric compatibility. Like if you go back to this Lagrangian, and if you focus in on the two derivative part of the Lagrangian, the only thing you have is a metric.
Yeah.
You don't have any other like torsion or other things.
But if you look at higher.
Good. Yeah. So for us, if we just start like this, we'll start out easy and we'll move up in levels as we go along. But just starting at the two derivative theory, the only thing we have is metric. So it's sufficient to use that as our definition of the geometry. If you have other things, say if you have fermions, then you do need other elements, not just metric. You need a connection as well. Good. But now just like put down some like these are just like some definitions derived from the metric. It's not connected with anything as of yet. And the way to connect this to say the dynamics of the particles is to look at how they interact. So with that, we can look at some like scattering amplitudes involving these scalars. So let's say scatter two scalars in, two scalars out. And this four particle amplitude. And if we just look at the two derivative part of the theory, forget about the potential, forget about higher derivatives for now. It only has two derivatives, meaning the scattering amplitude will depend on these Mandelson variables, which are the powers of momentum. And the prefactors will be the curvature in field space. That statement it's kind of non-trivial because it's saying like if you take the Lagrangian and just calculate iteratively in a fixed field basis, you get some amplitude with some coefficients. Those coefficients are precisely the like things you can get from the definitions in GR, the definition of the curvature. This is like a check that this makes sense to consider that, namely, the fact that they show up here means that this geometry is a useful notion to think about. Yeah.
So this is scattering amplitudes.
Yes.
What is the nature of this reflection?
This is a two, so yeah, good. So let's do like simple things first, and then we'll like gradually expand. Let's just start with this Lagrangian. Drop all the dots, all the height of the terms, and drop the potential.
No potential.
Yeah, just for simplicity for now. The only interaction mergers we have are two derivatives and some function of the scalars out front.
Okay, now I understand.
Yeah. And the statement is that in that theory, like with that like generic like non-linear sigma model theory, all the scattering amplitudes will be captured by like this definition of the curvature in field space shows up here.
Sorry, but amplitude, physical amplitude is invariant under field definition, right?
Yes, good.
Just a moment. And the way it's written here, in terms of curvature, it's not evident that it's invariant.
That's a very good question. So I'll just repeat the question from Zoom to the room. The comment was that scattering amplitudes are invariant under field definition, and that's not made manifest in this way of writing it.
Yeah.
So, yeah, good. So first comment is that, and the fact that the scattering amplitude depends on the curvature and not, say, the lone Christoffel symbol by itself, is the first step for, like, this is a covariant object, while the Christoffel symbol itself is not covariant. So that's why all the Christoffel symbols has to group up into the curvature. Second comment is that this is the like flat tangent space expression of it, which like goes from like being covariant to being invariant. And yeah, and that definition is also when you square this, all those indices become contracted. So in the cross sections also it's invariant. Is that helpful, or any other comments?
But not the amplitude itself. The amplitude, the way it's defined here, I mean, it is still covariant but not invariant, right?
Well, yeah. So it's covariant, but with respect to like flat tangent space indices, not the curved space indices.
Okay, but still, let's say I did some redefinition, okay, field redefinition. I'd like to check that I will get the same amplitude as before, right?
Yeah.
And I'm just trying to accommodate it with what you are writing.
Yeah, good. And this is also the expression evaluated at the vacuum. So
Yeah.
if you do calculate in one field basis and you change the field basis with say phi goes to phi plus phi squared.
Yeah.
Those phi squared dependent pieces will drop out in the expression of the amplitude and also in the expression for the curvature at the vacuum.
I think what he's missing is that you're already in the basis, which is the Riemann normal basis. So you've gone to the set of coordinates where locally it's flat.
Yeah, so I'm good. So you can calculate it in not Riemann normal coordinates as well, but the full amplitude will have. Yeah, I didn't put this in because I thought it was too technical. There's a difference between these indices, these capital IJK, and these lowercase IJIs, in that you go from like the manifold to the tangent space.
That if it's the original indices, then it doesn't look invariant. But
Yeah,
once
yeah.
you go into these indices, it is.
Yeah.
Yeah, exactly. Yeah, so it's in the tangent space because of these like lower IJK indices.
But it enters in definition of the amplitude, because when you define what you call physical amplitude, you already kind of change it. No, I mean, should accommodate what you call asymptotic fields, right? So it changes this altogether. So you still could have an expression which is explicitly invariant, and after applying this, right?
Yeah, good. Yeah, so the statement here is that like the correlation functions, like the correlation function of the phi's have some phi indices, the scalar field indices, while the amplitude has these like locally flat indices, which is taken care of in the LSC procedure when you go from relation functions to asymptotic flat amplitudes.
Yeah.
Yes,
Yeah, they're included in there.
yeah,
These are technical, this is not, one, not going.
yeah, these are tetra. Yeah, good. Yeah, because you go from, it's a way of like sort of normalizing your fields. You can like pick a frame where you have tetrads, which automatically flattens the field. That's what it enters in the scattering amplitude here. Let's proceed. And if we're happy here, or if we're not happy, we'll just proceed anyway. Let's look at the next simplest case, namely 5-particle scattering. Again, just from this two-derivative theory, it depends on these pies of momenta and these Mandelson variables. And the coefficients of all these, there are a few more terms, but not too many. The coefficient of all these terms are, again, covariant or invariant tensors in field fit. There's the covariant derivative of the curvature in this tetrad frame. So the take-home message is that all these scattering amplitudes depend on these geometric quantities. But this is not a new statement, it's a very old statement. First place I saw was from Volkmann 73, where he calculated all these scattering amplitudes for a non-linear sigma model. This is just a rehashing of that. Because amplitudes are invariant in the field definition, naturally depend on these geometric quantities, like this.
Yeah, to clarify, this is taken.
Yeah, so this is not a postulate. I'm just saying, like, take your Lagrangian, calculate in your way, and get some expression, then calculate these curvatures from the GR wave, right? And you'll realize that these things are equal.
It's like a posteriori, the check a posteriori would be equal, but when you like prove
So like the easiest way to see that this is true is that you can go to a basis where, well, the real normal coordinates, where the metric itself is expressed in terms of curvatures and covariant curvatures. And then you can, with that plus invariance in the field definitions of the amplitudes, you can see that these are oriented.
Is it possible that you can multiply by this, say, A4 or A5 by corresponding number of phi to make it explicitly invariant?
You want to contract the indices with?
Yeah, right. It's a question.
So these naturally have some flavor indices. They just label the different species of the amplitude.
Okay.
Yeah.
Yeah, but field are numbered by the same indices, right?
Right. You can contract it if you want with some other auxiliary variables, but as written, they're just some tensors.
No. I wonder if I contact with, say, phi I1, I2, I4. No, I mean the way it's written. Could it be interpreted as an invariant expression? Because then it works in any basis, no? I want just because it's covariant. I'm trying to find whether you can read off invariant.
So, for instance, we can compose the initial states and final states in terms of the representation of the flavors. For instance, you can think about the flavor single scattering to the flavor single state, and then that means that you contract the index by the delta ij, and you will get invariant. So, only you can do that.
Yeah, but you can also just like have some states which have some flavor label. This is just say like keeping track of the flavor labels as in tensor. Yeah.
Mm-hmm.
Some invariant point, and then you response some flavor.
Yeah, but then it's natural to ask. I believe what I'm asking that why you would not contract it with this flavor label field, right? Then to make it invariant.
But you can contract it with many other tensors as well, Arkady. You could also contract it with another Riemann.
No. Just a moment. We are talking about the amplitude, right? The amplitude contain those fields. It is amplitude, for example, 2 goes to 2, so 4 field, right? So I like to write this 4 field explicitly, because here it's not written.
But if you're just checking invariance, can't you just contract it with anything?
No. What means contact with anything? Because you have some number of field, right? 5, and for each combination of choice of field, you have this 2 by 2 amplitude, right? So here it is particular. So in this way, in principle, you have kind of some number of 2 by 2 amplitude, right? If you have number of flavors.
No, yeah, I understand.
What are you gonna get from contracting?
Yeah, it's an S matrix, right? It's a matrix.
Yeah.
It has different, like if you scatter one particular scalar versus other scalars, that's different entries in the S matrix.
Yeah, right. And then it's natural just to convolute indices of field with indices which are right in the amplitude, right? Because amplitude is defined by the amplitude of this 4 particular field.
I don't know what you get from it. You can multiply it by pi I1, pi I2, pi I3, pi I4 on both sides. But then what?
Well, I guess Arkady saying that that's what appears in the S matrix. 'Cause you've got
Yeah. Then it would be we can write as a convolution of A4 with this 4 field, and then then it's up to you to choose which particular flavors you interested to consider for scattering amplitude, right? But the expression would be in this way. Look at least as invariant in flavor space. No, because first is vector and R a tensor, right? Riemann a tensor.
Yeah, if you want to contract it, in fact, I'll write them as the 3 indices here.
Yeah, right. But it means that you choose those indices. It doesn't contradict to what I am asking, right?
This is a particular basis, Arkady.
Right. A particular basis is it's okay. You are writing the answer, but in this particular basis, you still have number of flavors.
Sure.
But he just wants to see the invariant of the amplitude.
Yeah.
Element.
Because then it's in any basis, because you are changing the basis, you are changing your R and you are changing your phi, but the amplitude A4 convoluted with phi is the same.
But he would then multiply by capital I, by capital J, and then.
But then you have to put back the tetrad.
Yeah, exactly. So we should probably move on.
Yeah.
So when you discuss the amplitude like a scattering by potential, not just.
It has interactions, but the potential is for now it's 0.
Okay, but discuss that later.
Let's move on to see if we can if we can. Good. So this was just to say that these curvatures and covariant curvatures show up in amplitude.
By the way, just quickly, I forgot to say, is that Volkov? There's no supersymmetry there.
Good. Now this is just some non-linear sigma model.
Yeah, he did
scalars.
Yeah, he didn't do Susie.
It's not well. This is just for scalars. Yeah. Good. So let's now turn on some other interactions. Not the potential, but these higher derivative interactions first. Now, if we look at these like 4 derivative interaction we had as an example, the pole point amplitude that depends on the 4 derivative interaction has now 2 of these animal stems, 4 derivatives, and the coefficients are just this tensor by itself, because it's like this one is equally like covariant as the curvature, just because lambda is a tensor. And then for 5 particles, we again get the similar kinematics, but the prefactors are the covariant derivatives of this 4 index tensor. This covariant derivative sees all these 4 indices here. So again, the amplitudes depend on some geometric quantities. For the covariant derivative here, it makes an entrance. If we like look at some scalar theory, we look first, we have two derivatives. And then if we get four derivatives here, it's the lambda with four derivatives. This one will be its independent tensor. This is some other coupling.
So
That's multiplying with four derivatives. Well, as of yet, it's just some other tensor in your theory. The lambda itself is a tensor, but at 5 points it will be the covariant derivative of the tensor. And that covariant derivative depends on Gij.
Also, like, to make sure I understand this lowercase I notation. This means you've chosen like a local flat metric. And
Yeah.
so these covariant derivatives are actually just normal derivatives, like just partial derivatives.
Well, they're not partial derivatives, but they're like everything is like locally flat. You have tetrad frame. Yeah, you don't need to like there are like if you expand this out, there are some like indices here. There's some you can pick a frame where the Christoffel is 0, but you don't have to.
Okay, you haven't necessarily picked the framework for the Christoffel.
Yeah, this is just any frame, and then you.
But
What should
Christoffel could be zero, but the derivative of the Christoffel.
yeah.
but you new tens lambda which you introduce, is kind of indeed kind of independent quantities with independent on metrics, right? Because and again it implies that they are tensors, right? So you're implying the lambda are tensors in field space, right?
Right. And then you can track that tensor with some tetrad fields, which goes to the tangent space.
Right, but so it's similar to before. So you still can contract them, but it's additional to the metric, right? It's a new tensors.
Sure. Yeah. It just said that you can rotate your flavors around. That's like orthonormal rotation matrix.
No, but the flavor is the same because this lambda with 4 indices in convoluted with 4 phi. So with 4 d mu phi. So this is the tensor is the same sense as metric tensor.
Yes, it's the same. Like the amplitude itself is the same kind of tensor. So it's just it's a sum of these two things.
Yeah.
That's right.
But the fact that you chose a locally flat metric, that does mean that the Christoffel symbol are 0, just like but like
Yeah, so
my period, so it's not just
yeah, all this means is that you can calculate these quantities in any frame you want, and at the very end you can track it with some locally flat frame.
Yeah, and I'd like to notice that what you're calculating, it is kind of a 3-level diagram, not more.
Yeah, this is still tree level. Yeah.
Yeah, I mean, no. Yeah. So the kind of this. No, I mean, at 3 level we are not expecting any deviation from field definition. I mean, from invariance, right? Because it contains no kind of saddle point about calculation.
I'm not sure
No, I mean that if you start to calculate, say, one loop in this order, then the expression would be different, right? And then it would be involving, say, regularization or whatever. At the level you're calculating, there is no any questions of like this, right? Everything is well defined.
Yeah, at the very end, there are some one loop calculations in RG. So we'll
Yeah.
see. Good. So if we are happy with this point, not sure, but let's just march on. First statement is that scalar amplitudes depend on geometric quantity. But that's not all the geometry is doing for us. Namely, it's not that individual amplitudes carry this geometry, but also you can find relations between amplitudes from this geometry. And that shows up in form of soft theorems. And a soft theorem is just taking a scalar amplitude, and you take some massless scalar and send it incremental to 0. And if that's universally related to some other low point amplitude, you can call that the soft theorem. So if you have this theory of scalars with no potential for now, the statement is that the soft limit of the amplitude with n+1 scalar is equal to the endpoint amplitude acted upon by a covariant derivative in field space.
Why you think it's a new soft theorem? Scalar symmetry was based on this.
So I've seen results on using this in special, like you can relate this to other known theories, but I've not seen this one written in paper. If you have a paper,
I think it's wrong. I think that all this relation between different number of soft pions were derived from chiral theory. You do not need anything else.
so I've not said anything about symmetry as of yet. This is just a statement about a generic scalar theory.
No, it's about symmetry because you are discussing relation between in this particular, say, chiral theory. Example you chose is a chiral theory, right? Essentially, and in the chiral theory, all this low energy theorem were derived from this chiral symmetry itself. And what you are writing is particular example of this.
Well,
Take pion chiral Lagrangian, you can check this.
the pions are well known to have an
Yeah.
average number. And that's, of course, is based on the chiral symmetry breaking pattern. Here, I'm not inputting that yet. But
Okay, but then your deriving amplitude is wrong because then there is no statement that it is second order in momentum because then there is no limitation to produce new terms. If chiral symmetry is not there, then say, for example, mass of pion could appear just in perturbation theory.
Sure. So
Okay, so then you are implying the chiral theory is there. Chiral symmetry is there.
Because you have massless scalars here.
Is it?
That's all I can't say.
Yeah.
So I'm saying there's massless. This is a theory with some massless scalar.
So it's not any theory of scalars, it's massless.
Yeah, but it's any. I haven't constrained the couplings in the rest of the amplitude based on the symmetry. That is, as of yet, unspecified and not inputted into this statement.
But isn't there an accidental symmetry that there's shift symmetry here?
No, but look, this theory which involves a relation between different number of particles implies that it is chiral symmetry because you're adding particle with zero momentum and you are saying that it is associated with the symmetry of the theory. It is definition of chiral symmetry.
So we'll see that this is not only valid for chiral symmetries, but more general.
Okay, if it's not about chiral symmetry, then the object you are discussing does not exist.
This is just some staring amplitude with scalars. It's not.
There is no this Q goes to zero additional scalar because it's not there. Let's say that it's a massive particle. What you are talking about then?
Yeah, I'm saying.
But it's massless.
I'm saying if you have a massless scalar, you can take its momentum to zero, and then you just look at how these staring amplitudes behave.
No, but then I'm insisting that it is a chiral symmetry.
Yeah, it's energy and momentum pointed to zero. And then you can look at how it's related to other.
Yeah, no, look, I mean, what is written that you have a kind of operation in which you can do, and this operation it is like producing, say, zero energy particle, right? I mean, additional one. This implies that it is a kind of symmetry theory and like a shift, right? You have a shift symmetry. Shift symmetry, it is chiral symmetry.
Maybe we can see some examples, and we can.
Okay, let him go on.
Let's uplift to say.
No, but look, when you are doing kind of a claim that it's a new soft theorem, it is what I'm reacting to. So I'm sorry that to interrupt.
Yeah, no, it's fine. Like you can. I'm happy to have many objections. So. This was in the example where you have no potential. If you say you have a potential, this relation doesn't hold anymore, it gets corrected by this additional term.
No, but the object doesn't exist. Because imagine that you have a massive particle. What means your amplitude at q goes to 0?
I'm saying step one, if you have a massless particle, then you can,
But potential doesn't preserve masslessness of particle.
yeah, I'm making, to make this, to discuss a soft theorem, you need a massless scalar in the theory, or massless particle in the theory. And I'm saying, assume you have at least one of these soft scalars, then you consider this limit.
No, but look, if you manage to introduce potential and keep particle masses, I'm saying that you preserved chiral symmetry.
It's not just chiral symmetry. Chiral symmetry is a special case, right?
No, not a special case. Any shift symmetry in the field, it could be called chiral symmetry. It's not a special case.
Well, I'm saying here, if you have a shift symmetry, you wouldn't naturally have this potential. I'm saying you can have a potential as long as you have some factor.
No, okay, yeah, but so then it means that you managed to introduce some potential which preserves this shift symmetry. If you believe that mass doesn't appear, right? You should choose, right? Then if the potential exists, then it is still. No, I mean normally you add mass term, chiral symmetry is broken, right? If you're thinking that you can add something which does not break kind of shift symmetry, then okay, then we can discuss it. But then I would call that chiral symmetry in some chiral symmetry is still there.
Yeah, we will connect this to symmetry shortly. Maybe that will be happier with that. But just as of now, it's okay. Let's just take this as a statement that if you take the soft limit of the amplitude, get the covariant derivative out on the other side. And if we just look at that statement, and you can see if it skip that because I think it's technical. We'll just look at examples and see if what I'm saying makes sense at all or not. Okay, and then we can come back to this question about symmetries. Let's just look at the amplitude we had before, namely first the two derivative theory at 4 points, and we will send particle force momentum to 0. This is the 4-point amplitude here, and depend on S34 and S24, which both vanish when P4 goes to 0, meaning we get this soft limit equals 0, which is consistent with it being equal to the covariant derivative of 3-point amplitude, which itself is 0 in this case. But at least like the first check that it passes.
Okay, but in this particular example you are given, you can recollect that it's exactly what chiral symmetry was saying.
Yeah, I'm just saying let's just check in some examples and
Yeah, you know, I agree, but your claim was about new soft theorem.
well, let's make that as like a let's investigate whether this makes sense, and then we can return back to the discussion of symmetry. So for all to make sense, you need to at least like not be violated by the examples we have looked at.
And the first one is.
Yeah.
This is obvious why that right hand side is 0.
The 3-point amplitude.
Yeah. Because you didn't.
For two, if you have just this interaction
Oh,
with
yeah,
two
yeah,
derivatives,
sorry.
cubic.
Right.
Yeah, the only
In these coordinates, yeah.
yeah, only thing you have is like a constant. Let's look at 5 particles and see what happens here. So we'll take the soft limit of 5-point amplitude, then particle 5 is not 0. What's written in this parenthesis is 5 particles amplitude here. The first line depends on S45, S35, and S25, which all vanish when particle 5 momentum goes to 0. As is this like last term here. And what survives is like the second line, S34 and S24. But also the coefficients here depend on the covariant derivative in particle 5's direction. So you can put that on the outside and see that what you have in the bracket here is just the 4-point amplitude. So here you get that the soft limit of the 5-point amplitude is the covariant derivative of the 4-point amplitude, which was what the soft theorem was saying.
Do you think it's a Newsov theorem?
Let's pin that to the wall and we can.
I do not think it's a Newsov theorem.
That's okay.
It's certainly a normal chiral symmetry.
So what's new is that if you have a potential, which I haven't seen from chiral symmetry, you can also do this for this theory. Namely, you can take a potential with, like, say, just a pure potential theory, 5⁴, which is no chiral symmetry. And if you send that soft limit to 0, you need both pieces of the soft theorem. You need both the covariant derivative piece and the cubic pieces with these factorization channels. Now, this theory at 4 points of the potential is written out here, but it is.
And you think that it is a new theorem?
Well, this one is for 5⁴ even, which is not a chiral symmetry.
I disagree. But why it's not a chiral? You can consider potential as perturbation, and you can apply chiral symmetry considering first order perturbation. No problem.
Okay, that's
So in this way, it did not show up as a new theorem, because you still can be in basis of chiral symmetry, and you would still can consider potential as it is here as perturbation, right? Then you can consider what is related. I mean, as chiral symmetry constraints in the presence of perturbation. I mean, because it has at least a first order in V, right? I mean, everything.
so what's kind of different in this case is that if you have a symmetry, or should I?
It's not. It is potential. It's also characterized as an object of chiral symmetry. It's potential breaks chiral symmetry, right? But it is like, no. I mean, you introduce V, say particular V, right? And you formulate what is the transformation of potential under chiral symmetry stuff, right? So in then you can still apply chiral symmetry to the object which are, no, I mean, like external breaking of chiral symmetry, right? But like in perturbation theory, in the external breaking.
Yeah,
So-
I'm not.
So I'm not trying to argue with your theorem. I mean, it's not that I'm in agreement that it could be the case. But what I'm trying to say is that it would be not new as compared with kind of standard chiral symmetry derivation as well.
Yeah, again, I have not said anything about symmetries. I'm only running this off a notion of field basis invariant.
Okay, but when you apply it in this way, and when you're relating amplitude with different number of particles, it is by definition chiral symmetry.
Okay, I think everybody agrees we should go on now.
Okay. No, look, you should delete me out of the public, right? And it's easy to do.
He's not allowed to use the word new, okay?
Okay, good. So let's move on and look at an example of whether this makes sense, namely this four-drift interaction. So again, if you have 4 points, take some top limit, this whole thing vanishes because all these depend on particle force momentum, which again is consistent with this covariant acting on the low point amplitude. And if you look at 5 particles and you take the soft limit of particle 5, you get the soft limit of this object. Now, all the things like which are written with cyclic conveniently, they vanish in the soft limit because you will have some S that depends on particle 5. This thing survives, and you see that all these coefficients depend on the coefficient here, with the curvature, or not the covariant derivative in particle 5 direction. Again, it's the same as the covariant derivative of the low point amplitude.
So I think it's, if I go to zero, then you follow I think you assume every parameters has this.
So I always need this particle, which I'm taking south, to be massless. Otherwise-
Other parameters.
Yeah, so in the previous example, we did have a potential.
Yeah, so that's the,
So here there could be masses on the other particles.
Yeah. except for this example, all the other examples, all the parameters.
Yeah, yeah. This is just a bit build some intuition of how.
Because otherwise S24 will
Yeah.
vanish. Because you need two split.
Yeah.
So
Yes.
that's important.
Yeah.
And for this example, is that only turn on 5-4 or you turn on all?
I'm turning on some potential which has some massless mode.
Yeah.
There could have some arbitrary cubic, arbitrary quartic, arbitrary quintic form. And it can allow masses for the others expected. And still you get this be consistent with the covariant derivative. The low point amplitude here. Okay. Now, what about older stuff? I have some comments saying that it's not new. Well, it's related to something that's well known, namely for a theory of pions. We do have a software. We have namely the Adler zero, and the Adler zero says that the self limit of the endpoint plus one particle amplitude vanishes, it goes to zero. And for this to be consistent with it also be equal to the covariant derivative of low point amplitude, that requires some to bridge this gap, because this is not the same as this generically. And the resolution to this is that, like, in terms of the geometry that we were discussing before, for the Adler zero to fold, then the covariant derivative of the curvature needs to be zero. Like, the curvature needs to be covariantly constant.
Yeah, Andreas, I'm sorry to that again, but look, it seems to me kind of internally inconsistent, because we start from the point that amplitude of scattering does not depend on field redefinition. So we are talking about amplitude which are field redefinition invariant. They are not dependent on and now for this field independent definition amplitude, there is a relation between amplitude with different number of external lines, like this Adler condition, but there are other conditions for higher. So in this way, when you are saying that it is related to this kind of geometric interpretation, I think it's cheating. Because either you have a relation between different amplitude and there is this kind of specific shift symmetry which relates amplitude with different number of external particle, or and it's irrelevant to the way we describe it, which particular field definition we are taking. So I think that it's, I mean, I cannot put it in my head, kind of consistently.
It's hard to be both well-known things, which is not new, and inconsistent. I'm not sure which one is.
No. But you are claiming that it is associated with this the discussion of invariance in configuration space. I'm saying that the real relation between amplitude is different number of particles. It is chiral symmetry, or you can call it chiral symmetry, whatever. It has nothing to do with field redefinition, because the amplitude we are discussing are independent on field redefinition, right? The amplitude, what we call physical amplitude, are independent on field redefinition. So they are, say, 5-particle and 4-particle amplitude are the same in any field redefinition.
A few steps between there. Like the first saying, the amplitudes are field definition invariant. Like leads
Yes.
depend on geometric objects like the curvature, and not on, say, the Christoffel symbol by itself. It does depend on the geometry, which is all where the.
No. It is about checking that field redefinition does not change the amplitude. The final amplitude of scattering does not depend on the field redefinition, and I think that we did agree on this. So the way you are writing this, okay, could be different. I don't mind, but the fact that physical amplitude is the same with any field definition, no, you can analyze how it goes. It's okay, but the amplitude is the same. So the relation between redefinition invariant amplitudes, I mean, it is some particular relation, and say this shift symmetry is essentially, no, I mean, in this particular case, it's a chiral symmetry, but generically you also can call it chiral symmetry if any relation of this type exists. It could be in different order, whatever, but it's by itself. I do not see how it's related to the notion that amplitude do not depend on field definition.
Well, the statement is that it depends on the geometry through the covariant derivative, which actually that's part of the key here, because
Yeah. No, that's why I'm trying to understand it. But if the amplitude does not know about field definition, how relation between the amplitude would be influenced by this?
It does from the examples we saw that you can evaluate this covariant derivative acting on it. And what is this actually doing? It's saying that the soft limit of this higher amplitude is related to like a nearby amplitude, like it's sort of it's a shift.
No, I think that you are essentially doing different stuff. You are effectively introducing this kind of shift of the field, you know, this kind of in the space of field, and checking what relation are associated with this shift of the field. It's not about field redefinition. It's about indeed relation between amplitude, I mean, with a different number of particles, and it is physical symmetry, whatever you call it. So I think that you are just hiding in your formalism the stuff that which is I would call chiral symmetry.
Good.
But let's move on, because otherwise, I think we should move on.
Patty, it's almost an hour in and I don't know.
Okay, no, no, look, no, it's my apology. I mean, I agree that I should not, but you know, I hesitated. Maybe I didn't need to participate on distance, right? So Andreas, my apology to you. I'm sorry that I am.
Let's move on.
Sorry, can I also ask a question here? So people usually talk about killing vector when talking about symmetry of target space, right? So is that related to your now or
Let's go to the next slide. Yeah. Yeah, good. So now we'll all be waiting for it. What does this have to do with symmetry? That's the thing we need to answer. So let's look at this a theory where we do have some non-linear realized symmetry, right? We have some naturally some say some scalars that transform under symmetry by in a non-linear way. This transformation can be viewed this way. So you have some scalars, you shift the scalars by something, which in general can depend on the scale themselves. And this will be the symmetry generator or the killing vectors. This is related to, say, chiral symmetry break. Now, if this one has a constant piece, this killing vector has a constant piece, then we say it's non-linear realized. And with that input, if we say we have a non-linear realized symmetry, we can contract it with the relation we had from before. We'll contract the open index here with the killing vector, and we'll rewrite this as the covariant derivative of the amplitude of the relation we had. Now, because this K is a killing vector, we can use a property of the killing vector, namely the leader that vanishes, which effectively swaps the covariant derivative from acting on the amplitude to acting on the killing vector itself.
And you can't go to a basis ever where K is a constant.
A constant?
Yeah, let's say you went to another basis. Could you always rewrite this into another basis where K is a constant?
In general, I don't think so, no. Because it's good. It's like generically you would expect there to be higher order terms.
And you don't think that there's a transformation which would, in some new coordinate where it would be a constant, and this would come back to Arkadi's point.
Yeah, it's like you can say that you have a symmetry, which is like just a constant shift, right? If that's your symmetry, then you can still do this. That's a specific way, specific field basis expression for K. I'm not sure if in a generic symmetry breaking pattern that you can do that. But it also doesn't commit to field basis. This says whatever K you have, you can write it this way. And now we have done something which is kind of nice, because rather than having this soft limit being equal to the differential operator acting on amplitude, which means it's not just the amplitude itself, it's like some operation on the amplitude, which effectively shifts us away from where you're at. It trades that expression for this expression, which has the amplitude at the same value, at the same band as before, just multiplied by this matrix. And this is like a much more familiar version of a soft theorem, where like you have amplitude equal to the amplitude at the same point in field space. And this ties into, say, some recent work by the Schiffman and collaborators, which discussed some soft theorems, which had a non-vanishing soft limit. And just to like write this back to the pion case, for the pion case, this combination here happens to be 0. That's where you have a chiral symmetry. It is a coordinate independent way of imposing the symmetry break pattern for pions.
Why was it important that it's not linear? Like you said that just means it has some constant.
Good.
You're just being indirect.
Yeah, good. So if you have if it's linear symmetry, then you have no constant piece here. So this equation, right? You have you do have the right hand side, but the left hand side is a 0. This whole equation is valued at the depth. It just means that this one is 0, and just get the normal on-show identity relations along for this amplitude. Just like this sum equals 0. Right? That's when you have like a linear symmetry. It just relates it like the same amplitude itself. Okay. Well, if you have a non-linear symmetry, it relates like higher points to lower points. Good. I'm not sure how much time I'm allowed to get.
You can keep going. Just good.
Good. Okay. So we can not turn it crank. Let's forget the new if you don't want the new anywhere in the discussion. Well, we consider a double soft limit. Because 2 particles going soft at the same time. Like if you do it in the sequential order, you just get the single soft limit twice. But if you do it at the same rate, you get something new. Namely, you get the double soft limit of the amplitude. M plus 2 point amplitude is equal to this expression. And the second expression, the second term is like the thing you naturally would expect. It's like the thing from like a Taylor series expansion of a function. It's a symmetrized covariant derivative. But you also get this first term, which is this ratio of kinematic factors times the curvature in field state times the amplitude. This is then like connects back to the double soft limit for pions. So pions, second term is gone.
But you are referring to 0.8, but look, it was in the previous century, because say the random derivation of pi amplitude involves this limit, right? You are talking about. So I mean, you can generalize it for other cases, but it was already used, long ago.
Yeah. So for pions, this is maybe that.
Yeah.
Yeah, that's fine. You can put whatever reference within here. The point here is that this is like it adds this term which is there in general, and it's gone for pions. Now, if you do
Just for consistent double soft limit, I always care about this. What's the meaning of taking the sequential?
Sequential,
Yeah.
Yeah.
sequential stuff.
it means that you're taking Q1 0 first and then Q2 at a slower rate.
Yeah.
0.
But does it give me any insight about the theory?
It gives you like the commit, or you can do that like that once and twice, minus the other way. Like it's the commutator of the covariant derivatives. Like you get curvature out, but you don't get this ratio of -10.
I was just trying to take scenario. If I want to take a consistent double sum, I probably want to take it at the same rate. I will always worry about it.
Yeah, so that's what you have here. If you do it same rate, so you see this ratio, it's like exactly it's order 1, even though the flow terms go to 0. Now, if we do triple south limit, like 3 of them at the same time, then you can also write down some soft term. Now it depends on like multiple terms. One term is this triple covariant derivative of the amplitude, like that. Term in the Taylor series, you would expect. Then you also get, say, this ratio of Fresnel times curvature times the covariant derivative, or the covariant derivative of curvature, and then plus this one. And these all terms are 0 for pions, but they're non-zero in general. And you can keep on going, so it just probes deeper and deeper into the structure of the amplitude.
No, I do not think that it's true about triple, because say, in my time, I was involved in the soft pion, for example, for K decay, and there, was 3-4 pion included. So in this way, this type of relation were used. So saying that there is no analog for pion, I disagree.
I was saying, yeah, for pions, it's 0.
No. But you can when you introduce, say, like K and decay, then you have kind of again, you see, you have perturbation, and then you can use it.
Yeah, if you're just pions, then the whole thing is 0.
Right. But as I said, that K goes to 4 pi, for example, or 3 pi. Then K it is kind of not pion, right? It is kind of, but I mean, you still can consider this. When you introduce this, I mean, we are going from SU2 to SU3, right? And K and say massive and pi and masses, you can still get relations similar.
Okay, to my knowledge, I haven't seen this expression written out elsewhere, but if you have someone who can. Now, I think just because of time, I will have to skip a chunk of this, and I'll go to this discussion, namely loop effects. I was going to talk about gauge fields, but gauge field is too long-winded to be incoherent. So all the things we're discussing for now is just tree-level scaling amplitudes. So how can we get, like, say, a Willen loop effect into the story? Like, is there some notion of geometry which is there also at loop level? And yes, there is. In particular, you can calculate, say, the renormalization group equations in terms of geometric quantities. So here's just to show one example of how this shows up. So if you, rather than calculate the renormalization group equation of some coupling constants, you can equivalent group them into these curvature objects. So the Willen loop RG of this Riemann curvature depends on the Riemann curvature itself times covariant derivative of the potential, or this covariant derivative of the killing vectors with gauge interactions as well. So like they're all like covariant objects on both sides of the equation. Now, this was calculated using on-shell methods and scaling amplitudes. You can also calculate this with more like other methods. Sorry.
Could you use this result to find the RG equation of the metric?
Yeah, this is for the curvature, which is derived from the metric.
Yeah, but I mean, could you reproduce the RG equation of the metric, use the way to calculate?
Perhaps this way is like written out. It's for like each endpoint by itself. So like it's this is like 4 point interactions in 4 dimensions, I should say. So if you want to like resum this into like just one equation for 2 point interactions, it's kind of hard to see how you do that. But yeah, this is the curvature. You can also calculate like the covariant derivative of this, like the 5 point and so on. I'm not sure how helpful that was. Maybe this is more.
Because the 2 point interactions of you just throw away the effective. You just throw away the potential in the higher copy, then you just have sigma. And
Yes.
In the RG equation of the sigma is known. So
Yeah, in 2D,
huh?
which space and dimension are you working on?
Yeah. For example.
Yeah, so this is for 4 dimensions. For 2 dimensions, it's like the symbol is normalizable and so on. So that's which is true. Like the RG is like changes when you have like different space and dimensions, right? Because it becomes a normalizable theory. Yeah. So the RG structure changes depending on your space and dimension. But maybe like more along the lines thinking is that you can calculate the same RG from say like just effective action calculation, not using Onshot amplitudes, but just some other methods. And in that setup, you would calculate the second variation of the action, or these like betas are the fluctuations field, which you integrate over get the one loop action. And if you have a theory, say for if you can write your theory in this way, then you can calculate the one of epsilon part on loop from these x's and these new covariant derivatives, and we just want these traces of x squared and traces of y squared, with y as this commutator of these covariant derivatives. So if you're able to write the second variation in this form, then you can just apply this formula and get the RG from that. Now for scalars, if you have just scalars with 2 derivatives and a potential, then you can write the second variation in this way, where you have some covariant derivative with a metric, and then the eta, like the thing was x, like the eta squared term, depends on the covariant derivative of the potential, as well as the curvature tensor, Riemann curvature tensor, contracted with this d mu phi, d mu phi. These two terms will be the x. And then from this covariant derivative, you can calculate this commutator, where again the curvature pops out, contracted with this d mu phi, d mu phi, as well as some covariant derivative of the kilometer times the field strength if you have gauge state. Now we can uplift this whole story to include gauge fields as well, which is like a backstory which I didn't tell you at the time. But the punchline is that you can do a very similar variation of the action, where now your eta fields can be both scalars and gauge fields, and it will all be dependent on like geometric quantities. For example, this commutator would be the generalized scalar gauge curvature in field space, which depends on both d mu phi as well as the field strength here, as well as some generalized notion of result symbol. So you can just reapply the scalar expressions, but also a sum over scaled and gauge fields. And then you can take this and get something out of it, namely you can calculate it for a specific theory. This was for like a generic theory of scales and gauge fields. If you specify to the standard model, or in fact the field theory extension of the standard model, you can then just like specify what your scalars and gauge fields are, plug it into the formula and get some expressions out. And SANML, you have at least 4 scalars in Higgs doublet, so you can group all the gauge field in this multiplet, and you just add on higher dimensional operators to the SANML. Some examples of these operators you can add on are written here. So like I mentioned 6, you have some modification to the potential, you have some modification to the tutor of the interactions of the scalars, you have some modification to the field, like F squared, or the kinetic term of the gauge field. And if you go to like a higher mass dimension than mass dimension 8, then you again have more of these higher dimensional operators. So in general, there's a bunch of them, and it's kind of annoying to write them out explicitly and calculate with each individual ones. But the power comes that you don't need to. You just like take this and then reformat into a metric and curvatures, and then re-expand at the end. You can recycle the general formulas for the curvatures in this specific example. And just and we did this, calculate the RGE for the SANML EFT, including the mass dimension 8 effects. So the expressions like from here, say, depends on the curvature and field space, you then specify and plug in all the expressions and expand that, you get expressions like this, which is like a whole mess. But they're kind of easier to calculate because they're coming from some covariant and nice object.
We haven't had any formula.
Yeah, there's no fermions. I think there's many objections that I do, but I'll end there just saying with some summaries. So first of all, scattering amplitudes naturally depend on geometric quantities, as we saw in numerous examples. You can also relate various scattering amplitudes to each other using Sock theorem. And the geometry also shows up in, say, one loop RG calculations, as we saw before. And for me, like what I take away from this is that like, this geometry is it's important in the interaction of scalars. They're naturally there, and they're like generic in a sense. And sometimes it's useful to zoom out to see the structure rather than zoom in. So if you zoom out and not talk about specific theories, but what is general classical theories, you will see relations between them. And Sock theorems are very generic and not so special. And that could be true for other things. So, well, I'll just thank you for your attention.
Any further questions?
Andreas, I still like to formulate my comment. I mean, maybe that I believe that in this way, what you call geometry, you know, I do agree about geometrical meaning, whatever, but it is geometry, for example, in formulation of, say, chiral symmetry, or in gauge series. It is geometry of the symmetry, which does involve, of course, possibility to change I mean, field definition or whatever, and I do not think that, you know, kind of, no, so using this Riemann tensor, whatever, it is still particular form how to write the amplitude, right? And I think that all these geometrical features you are discussing, it is still could be interpreted as geometry.
Cardi, we lost you. We lost you there for a minute. You're going to have to repeat.
Somebody probably, can you see me now?
Yeah, we can see you now, but you're going to have to repeat it. He heard part of the question.
No, I was just trying to formulate the comment that I believe that it is geometrical indeed, but it's a geometry of symmetry of the Lagrangian in case of chiral symmetry, in case of the gauge, standard model symmetry. So it's okay to use this parameterization of the amplitude referring to Riemann or whatever, but it's I do not think it contains anything special besides geometry of the symmetry, and I believe that in this respect I'm different from. I believe I'm different from Andreas, your interpretation, but it doesn't mean that I am right, but it is my opinion.
Okay, so I would say that the geometry, like the starting point, if you just talk about the geometry in the scattering amplitudes,
Yeah,
that doesn't require any notion of symmetry because you can formulate it that way for any theory.
With or without it.
Yeah,
no,
with
no, 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 okay. And I'm saying that all relation you are talking about could be derived from geometry of the symmetry, not referring to particular, notion of invariance under field redefinition. No, no, I certainly disagree with field definition, but relation we are talking about are independent on field definition. So in this way, they could not be anything but certain kind of symmetry, and it is what I'm insisting on.
So yeah, again, I'm just going to repeat what I said.
I think it's
Like symmetries are great and they're super useful and constraining, but like the starting, like step 0, right? Now these amplitudes doesn't require any notion of symmetry. If you have symmetry, you can constrain it further and get
Okay. Once you found relation between the amplitude with different number of particles, I'm insisting that it is a symmetry, whatever you call it.
Yeah. So okay, I'll agree with you on this point that you can complain saying because I have a massless mode.
Yeah.
So that's naturally there if you have symmetry, and not there if you have no symmetry. I agree. So that is something special about having, like, if you have a massless thing, that's required for sure.
Yeah. Right. So in this way, you're referring to kind of this geometry of field space. It is still the way to discuss particular form of symmetry, but symmetry itself, it is still there. Okay, I'm sorry that I'm taking too much of your time. Sorry. Okay.
No, but it's I'm very happy for comments and other perspectives of this, and also like, okay, maybe I'll comment on this. Like many of these statements on this like geometry and so on, it's like a revamping of old knowledge, and there's a bunch of like things from back in the day which we like heavily rely on. So this is like this notion of geometry is, of course, it's not new, it's very old, but it's been imported into other areas, namely the Standard Model. It's extremely useful to capture things in this way. So there's like a vast treasure trove of knowledge that can be extracted to other things. Yeah.
So Andre, Andre had a question.
Okay, just learning a question about filter definition. So suppose I take just phi squared, just receiver, right? And I make the filter definition phi going to phi squared.
Yeah.
Then I get phi squared, which looks equivalent to the original theory, but to see that and then to apply your equations for amplitude and local flat basis, I should make the transformation phi going to square root of phi. And I'm just wondering if this is a good or this is an allowed transformation, because you take the derivative, you get the singular, the origin, it's good. Also, in other words, what the allowed class of.
Yeah, so I'm always assuming that you have a linear term. So
No, so you're going to answer. So I go ahead.
yeah, so like if you want these like transformation properties, like if you go from phi to phi squared with no linear term, then like this doesn't make sense. So like I'm restricting to the class where you have a linear term in the phi, because you need some overlap between the fields and the state.
You have to have phi as the first term. That is the answer.
So this covers the term of metric is like a higher dimensional vector, so this is I mean, if we find some higher dimensional operators, for instance, LSC, then eventually we want to UV complete, right? We want to learn UV theory. So can you also kind of formulate the possible UV completion in terms of geometry?
Yeah, good. So in 4 dimensions, these, as you were saying, these metrics, if you have a renormalizable theory, they're all like they're flat, like the delta AJs. So all these non-trivialness is coming from the higher dimensional operator. So that's like generic there for integrated out some modes. Like how you like conceptualize like integrating out a mode geometrically, it's not completely clear how you do it, because you have to go to like a highest dimension manifold to low.
That is kind of embedding this type of space into some class space.
Right. Yeah. In a sense, yes. But like in general, I don't have like a more concrete picture than that. you do get more, right? Say if just scalars and you integrate out some heavy scalars, because you have an extra scalar, you have a higher dimensional manifold, right, in the UV. And you integrate out to like a lower dimensional manifold.
I think I'm curious because sometimes it is better to add the gauge bosons instead of a scalar gauge. You compare, for instance, CPN was n minus one non-linear model.
Right.
You can naturally you will complete that by adding the gauge field instead of the scalar field. So I'm kind of wondering what characterizes this kind of features. And it should also be understood from people.
Yeah, no, I totally agree. So we haven't looked at any like what's there and how you view the complete and so on. But I think it's a natural set of questions to consider.
Yeah, so if we improve quantum in our theory, like what's your expectation like about those correlation?
Which, yeah, so like if you have fermions, like the basic point still holds that things are invariant under field definitions, including fermions. So the amplitudes will naturally depend on geometric objects. Now these geometric objects will now depend on also the fermion like flavors, as well as the scalars. And like for example, the 4-point amplitude, 2 fermion, 2 scalars, its coefficient is the curvature in the scalar fermion field space. So it's like some other objects. And but I think like a lot of this, like there's some details right in how you define that curvature, but like, the broad strokes here will still hold.
Okay, I think we've exhausted all the questions for today. So let's thank Andreas again. Thanks, Arkady. Thanks.
Yeah, no,
Yeah,
thanks for the question.
Yeah, I'm sorry that I interrupted, but look, I was thinking, I was involved in this soft pine, let's say, starting 1966. So I went through all this different amplitude calculation, whatever, and I'm thinking it was 1966, and later on, few years. So my PhD was actually about soft pines, and now look what is how many years did come. So it looks like I'm living too long. I'm sorry.
You're doing fine, Arkady. You're doing fine. Not a problem.
No, yeah. So I hope that but I gave you some problem because I.
Exactly.
So, my apology.
It's all good. Thanks a lot again. So I think we have to stop the recording now.
Yeah. Okay.
Okay.
Okay. Bye.
See you, Arkady. See you. Thank you.
I know about that. Yeah,